In 2024, a team in China quietly built something that breaks the rules of building. It is a new material that is 8 times stronger than steel and 80% lighter. Early tests show a piece of this stuff holding up a load equal to 12 adult elephants before showing any signs of breaking. 12 elephants held up by something you could lift with 2 fingers. That alone is amazing. But the strength is not even the main reason builders all over the world are paying close attention right now. The real story is about who controls the supply chain for whatever replaces steel in the next big shift in building. If you like videos like this, please hit the like button because it takes a lot of work to make these, and subscribe so you do not miss the next one. The details of how this material works are almost hard to believe. The answer has to do with a structure so tiny that it is built from atoms. To understand how a material 8 times stronger than steel became a real thing and not just a lab dream, you first need to know the hidden flaw inside the steel that has held up our world for 150 years. Why steel ruled the world for 150 years? Steel is everywhere. It holds up tall buildings, forms the hulls of ships, and provides the frame for cars. For almost 200 years, engineers have chosen steel, first because it does something almost nothing else can do at such a large size. It turns rock into a material that is strong, easy to guess, and endlessly repeatable. Engineers love steel because they know exactly how it will act under pressure. If you put a heavy load on a steel beam, it will bend a little bit before it breaks. That bending gives a warning. It lets people know they need to fix it before a real disaster happens. That single trait made steel the backbone of almost every major structure built since the 1800s. Think about a busy highway bridge. When too many heavy trucks cross it at once, the steel beams do not just snap, they groan and bend. This gives workers time to close the road and fix the problem before anyone gets hurt. Builders love steel because the tools and supply chains have been worked on for a century. The way of making it is safe and boring in the best way. A bridge built in Shanghai and a bridge built in Chicago can both hold the same weight because builders use the exact same math to build them. That kind of trust takes a long time to build. A single modern cargo ship can use over 30,000 tons of steel plate in its hull alone. That is about the same weight as 80% fully loaded large airplanes. A modern tall building can use over 60,000 tons of steel, which is like stacking 6 aircraft carriers into one frame. Steel earned its place as the king of building materials through 150 years of hard work. Governments love steel because they can make it inside their own country. They do not have to wait on rare stuff from across the globe. If a country needs a bridge or a ship, it can make the steel right at home. That makes steel a safe choice. It is easy to get and easy to use. But that power came with a hidden cost that almost nobody outside of science labs ever thinks about. Once you see this hidden cost, you cannot unsee it. The flaw is baked right into the tiny building blocks of the metal itself. For a long time, nobody had a tool exact enough to even see the problem, let alone fix it. Understanding this hidden flaw is the first step to knowing why a new material from China is making headlines. The story of steel is not just about success. It is about a ceiling that nobody could break. To see why steel finally met its match, we have to look closer at the tiny atoms that make it up. The hidden flaw baked into steel. Steel is made of iron atoms locked together in a pattern. No matter how carefully workers make the steel, that pattern always has tiny flaws. These are tiny gaps and mistakes that you cannot see with your eye, but they are very real if you look under a strong microscope. Those tiny flaws are exactly where cracks begin. This is not about steel being a little bit weaker than we want. It is about a hard limit on how strong any metal can ever become. No matter how you mix it or treat it, the tiny flaws will always be there waiting. This puts a cap on what builders can do. Think of it like a chain link fence. The fence looks solid from far away, but if you look closely, there are tiny gaps everywhere. If you pull hard enough on the fence, it will tear at one of those gaps. Steel works the same way. The tiny gaps between the atoms are where the metal tears when you pull it hard enough. Here are the numbers that make the flaw impossible to ignore. Standard structural steel tops, out at a strength of about 400 megapascals. Think of it like stacking 40 family cars on top of a single postage stamp. That is a lot of pressure. To get steel even stronger, engineers have to add costly materials like nickel or chromium. Even then, the strength stops going up, while the weight stays exactly the same. This makes a strange problem. A steel-framed tall building can spend up to 60% of its budget just fighting its own weight. The steel has to carry itself before it can carry anything useful. Every extra ton of steel used to hold up more steel is dead weight that does nothing for the people inside the building. Imagine wearing a heavy backpack full of rocks just so you can carry one book. You are spending most of your energy just holding up the rocks. This problem shows up everywhere once you know to look for it. Heavier structures need deeper bases. They need more concrete. They need more fuel to move the materials. And they need more energy to move anything built from them. A ship-built lighter could carry more cargo every trip. A building-built lighter could rise taller on the same base. An electric car-built lighter could drive farther on the same battery. For decades, this weight limit seemed permanent. It felt like a law of nature dressed up as a building problem. Researchers had ideas about how to fix it, but those ideas stayed on paper. They were dismissed as lab dreams that were too weak or too costly to ever leave the building. That was the ceiling that trapped builders for over a century, until a team in China found a way to look at the problem from a totally different angle. Building with carbon instead of metal. In 2024, a research team in China started answering the steel problem with real data. This data was harder to ignore than anything the field had seen before. It challenged an idea that had stood since the 1850s. The team worked out of the Institute of Metal Research at the Chinese Academy of Sciences in Shenyang. They also worked with materials engineers from Tsinghua University who studied tiny carbon structures. Their core idea sounds almost too simple once you hear it. Instead of trying to make a stronger pattern out of metal atoms, they decided to stop using metal atoms to hold the weight altogether. They built the material out of carbon instead. They arranged the carbon so exactly that it has almost none of the tiny flaws that cause ordinary metal to crack under pressure. Past attempts at making carbon supermaterials failed for one very clear reason. Earlier carbon nanotube fibers could be grown in a lab with great strength, one by one. But the moment researchers tried to bundle millions of those tiny tubes together into something useful, the links between them were weak. It was like braiding a rope out of unbreakable threads, using weak glue that fell apart the moment you pulled hard. The rope was only as strong as its weakest joint. Here is the part that makes this truly exciting. The Chinese team made a new way to lock the carbon tubes together at the smallest level. This moves the weight straight from tube to tube instead of relying on a weak glue layer in between. Picture threading thousands of tiny magnets so perfectly that they lock end to end into a single unbroken chain. There are no gaps, no weak links, and no slipping when you pull on it. Each tiny tube is perfectly lined up with the next one point. That single change is what makes everything else possible. Earlier bundles lost most of their strength the moment they were woven into something big. This new bonding method keeps almost all the strength of each tiny tube, even when you build something large. The lab samples measured a strength of over 3,000 megapascals. That is 8 times stronger than standard structural steel, and it weighs a tiny fraction of the same steel sample. A 1-meter strand tested in Shenyang kept its strength within a few points of the tiny samples that started the project. This mattered a lot. Many earlier lab materials looked amazing at a few millimeters, but fell apart the moment anyone tried to make them longer. This one did not. The science worked, but a strong lab sample is a long way from a material anyone can actually build with. The real test was about to begin as the team faced the challenge of turning a lab dream into something factories could actually use. Why cost does not tell the whole story. Here is the honest limit stated clearly before anything else. This new material currently costs about 40 times more per kilogram to make than standard structural steel. The making process still tops out at meter-sized batches. That is very different from the Mailiong steel coils that modern industry is used to ordering by the ton. But here is what that cost number actually means in practice. 40 times the cost per kilogram sounds like a deal breaker until you remember that this material weighs 80% less for the same strength. In places where saving weight directly means saving fuel or adding speed, the cost gap shrinks a lot. In some cases, the cost gap goes away entirely once you figure out the cost per unit of strength given rather than the cost per kilogram of raw stuff. Where the limit stops mattering is anywhere weight matters more than raw material cost. Most people never think about how much of a rocket launch cost is spent lifting the rocket's own frame rather than the actual cargo inside. In aerospace, engineers routinely pay extra of 10 times or more for every kilogram saved. By those rules, this new material is not costly. It is a bargain. Beyond raw strength, the material shows great resistance to wearing out. It survived over 10 million stress cycles in lab testing without any measurable breakdown. That is about 3 times what similar high-strength steel cables music can take before they start to crack. That resistance to repeated stress, not just one big push, is what turns a strong material into a long-lasting one. Think of it like a rubber band that can be stretched millions of times without snapping. That is what makes it useful for real-world jobs. One use already uses it today without waiting for costs to fall further. Deep-sea research cables have already started quietly switching over. A cable lowered 4,000 meters into the ocean carries the weight of its own length the entire way down. Every kilogram taken away from the cable itself is a kilogram of extra space for tools at the seafloor. Satellite tether systems act as a second early adopter for the exact same reason. Every kilogram launched into orbit costs thousands of dollars in fuel. A tether weighing a fraction of its steel equal is not a fancy upgrade. It is a direct cut in mission cost. The question was no longer whether this material worked. The question was which business would be willing to pay for it first. That answer arrived faster than almost anyone expected, and the first big test came from the bottom of the ocean, surviving 8 months under the ocean in Qingdao. In 2025, the National Deep Sea Center replaced a section of a steel research cable with a sample strand of this new material. They did this during a normal equipment swap on one of its long-term ocean monitoring buoys. Over 8 months of constant use at depths going beyond 3,000 meters, the cable showed zero measurable strength loss. The steel section it replaced usually needed checks and partial replacement every 18 months due to wearing out and rusting. This field test matched the guess perfectly. That matters more in the ocean than almost anywhere else, because ocean engineering has a long history of materials that do great in a controlled lab tank, then they fail within weeks once they face real ocean conditions. Seawater pressure and temperature, music, swings all work against materials at the same time. The salt in the water eats away at metal. The huge pressure pushes against every tiny crack. The changing temperatures make the material grow and shrink over and over again. A material surviving 8 months at 3,000 meters without breaking down is not a marketing claim. It is a real-world result, logged and independently checked. One senior materials engineer